Hello and welcome to this video. In this video we will continue our discussion on the topic recursion. Binary search. In this section we describe a classic recursive algorithm called binary search, which is used to efficiently locate a target value within a sorted sequence of n elements. Okay, so in this picture we have an example of a binary search tree. Structuring binary tree elements. Each tree has a special node called its root, usually drawn at the top. Each node is permitted to have two links to other nodes called the left child and the right child. Children are usually drawn below a node. Some nodes have only one child. A node with no children is called a leaf. Each node is called the parent of its children. The root node has no parent. Every other node has exactly one parent, and two nodes with the same parent are called siblings. So let us now try and understand the concept diagram. So there are two trees in this slide, and the tree on the left hand side is the binary search tree, whereas the tree present on the right hand side does not qualify as a binary search tree. We'll look into how to classify that, right? So according to our structuring rules, the key node here, we are considering the left tree first. So the root node has a value of 6. As you can see, that is the top node and it is having a value of 6. Now there are two nodes connecting or branching out from the root node. They are one is the left child and the other one is the right child. So the left child is having a value of 3 and the right child is having a value of 10. So it is important to note that the left child will always have values lesser than the parent node. For example, 6 is the parent of 3 of the nodes containing values 3 and 10, right? And also 3 and 10, because they have the same parent, 3 and 10 are siblings, right? Also, if you look at all the nodes present, so for example the root node has a value of 6, so all the nodes to the left hand side, for example 1, the nodes having the values 1, 3, 5 and 4, they are all lesser than 6, right? And all the nodes which are to the right hand side should contain values which are greater than the parent node. Okay, so again, if you go to the node having a value of 3, you can see that the left child is having a value of 1, which is lesser than 3, and the right child is having a value of 5, which is greater than 3. Okay, so if we now go to our tree on the right hand side, we have the root node having a value of 6, then we have two child, one is the left child having a value of 3, and then the right child is having a value of 10. This is fine. Again, if we go to the node having the value of 3, the left child is having a value which is lesser than 3, that is fine, and the right child is having a value greater than 3, so that is also fine, which is 5, right? Then if we go to the node containing the value of 5, the left child is having a value of 4, which is less than 5, that is fine, but the right child is having a value of 11, which is greater than 5, no doubt, but it is having a value which is greater than the root node. Okay, because these nodes having values 1, 3, 5, 4 and 11 should have values which are less than 6, but because in this case we have 11, so this does not qualify as a binary search tree, right? So let us now try to understand the search operation of a binary search tree. So in this case we have the element to be searched is equal to 10. So what happens is it goes to the root node, it finds the value, compares it, and if it is having a value which is lesser than or greater than or equal to, based on those equalities or inequalities, the further operation is determined. For example, in this case we have the target is 10 and the root node is having a value of 12, so obviously 10 is less than 12, so it goes to the left child, because the left child will have values which are less than 12. So it goes to 7 and it sees that 10 is greater than 7. So what it does is it goes to the right node. Okay, so because it will have values, the right nodes will have values greater than 7, and obviously 10 is greater than 7. Then it reaches 9 and still it sees that it is having, the target value is having a value greater than 9. Okay, so again it goes to the right node, and now on comparison the value of target node matches the value present in that node, which is 10. So then that value is returned. So this is how the search operation in a binary search tree takes place. Okay, so now when the sequence is unsorted, the standard approach to search for a target value is to use a loop to examine every element until either finding the target or exhausting the dataset. This is known as the sequential search algorithm. This algorithm runs in linear time complexity, since every element is inspected in the worst case, which is linear search. Binary search is among the most important computer algorithms, and it is the reason that we so often store data in sorted order. Right? Let us now look at how binary search works. When the sequence is sorted and indexable, we can use binary search. It works by repeatedly dividing in half the portion of the list that could contain the item until you have narrowed down the possible locations to just one. Step 1. Define two variables low and high, where low is equal to 0 and high is equal to n minus 1 if the array contains n elements. Okay. Also note that low and high are index positions. Step 2. Define a variable mid, where mid is the floor division of low plus high. So basically low plus high floor division of by 2. Okay. So for example, if we have say the low value of 0 and the high value is equal to 15, so 0 plus 15 is 15, and 15 floor division by 2 will give us 7, not 7.5, because what it does is 15 divided by 2 is 7.5. so then the decimal part is truncated, it is removed when we are doing a floor division. In this step 3, we consider 3 cases. Like if the target is equal to the data present in the mid index position, then we have found the item we are looking for and the search terminates successfully. If the target is less than the data value present in the mid index position, then we recur on the first half of the sequence, that is on the interval of indices from low to mid minus 1. If the target is greater than the data value present in the mid index position, then we recur on the second half of the sequence, that is on the interval of indices from mid plus 1 to high. An unsuccessful search occurs if low is greater than high, as the interval low high is empty. Okay. So now let us open the Jupyter Notebook and see the Python implementation of binary search. So we have opened the Jupyter Notebook. So let's see how to write our code. At first I'll define a function called binary search, which will have 4 arguments or parameters that I'll pass on to the function. The first one is the data, the second one is the target, the third one is the lowest index position, and the fourth one is the highest index position. Okay, so let us now first define what this function will do. So it will return true if target is found in indicated portion of a list. Okay, and the second one is the search only considers the portion from data low to data high, and this is high, and this is inclusive. Okay, so now let us write our conditions. So if low is greater than high, will return false. Okay, or otherwise Now what will happen is we'll start writing our actual code. I mean, these are all code only, but this is our when everything is set. Now we start our search. Okay. So first of all, we'll have to define this variable mid, which is equal to the floor division, the floor division of the low plus high. Wait, low plus high. We have this value and floor division of 2. So what happens is, suppose I have a lower index position of 0 and suppose my high index position is 7. So we'll have 0 plus 7 divided by 2 is 3.5, right? But when we are doing a floor division, what happens is the decimal part is truncated, it is removed, and we get only 3 as our return. So mid will be that value. Now if target is equal to data that is present in the mid position, we will return true, right? If suppose the target is less than the data present in the mid, or the data present in the mid index position. So what we will do is, first let me explain what it will do. It will recur on the portion left of the middle, right? So now again we'll return the binary search function. The data stays the same, the target stays the same, the low value is same, however the high value changes to mid minus 1. Okay. And else, if suppose else already includes if the target is greater than data present in the mid index position, then it will recur on the portion right of the middle, and it will return our binary search function, except the data remains the same, the target remains the same, but the lower position changes to mid plus 1 and the higher position becomes high. Okay, so this is our code. So let's see, suppose I have my data, or you can call it anything, like give it a name, suppose list values or nums, for example, say num, and define our list 1 2 3 5 7 9 11 25 34 43 57. Okay, say this is my list of numbers. Next I want to locate, say for example I want to locate 9, right? And the low position would be, it will be 0, because a list starts with 0 indexing, and my high value would be, so we have how many elements here? 1 2 3 4 5 6 7 8 9 10 11 elements, right? So my high value would be n minus 1, 11 minus 1, that is 10. Okay, so now if I try to call this function binary search and pass on the values, suppose this is the list, which is the data, then my target is this, which is equal to 9, my low value is 0, and my high value is 10. So let's see, we get a true. Okay, but if I try to locate a number which is not present, we'll get a false. Okay, so let us now try to I'll use a sketching tool to sort of explain you how this is working. So this is my list of numbers that is present here. So now we'll at first we'll write the index positions. So it is 0 1 2 3 4 5 6 7 8 9 10. Okay, So this is my lowest position, which is low, and this is my highest position, that is high. Okay, so now what it does is it checks whether low is greater than high. So in our case, the higher value is, or the value that is present in the high variable is 10, whereas in the low it is 0. So therefore this is not a problem. So it moves to the else statement. So now it calculates the mid value. Okay, the mid value, and the mid value is calculated by 0, which is low plus high floor division of 2. So we get 5. Okay, so the data that is present in the 5th index position is the mid value. So this becomes my mid value. So for example, now my target is, that we are looking at is, target is 9. So what happens is, because the target matches the data in the mid value, we want 9 and we are seeing 9. Therefore what happens is, we have reached our search, like the search result is out, and we have cornered the position of 9 and our program terminates, right? But suppose if our target value is something else, suppose it is 34 for example. So what happens is, because the target value is greater than the value present in the mid index position, so therefore what happens, we go to this condition where it is less. So this will be the last one. This else condition is basically when the target is greater than the data present in the mid index position. So our 34 is greater than 9. Therefore now we'll update, the data remains the same, this is my same data, but my the focus area changes to this part. Okay, so my new low becomes this value, this becomes my new low. Okay, and the high remains same, it doesn't change, right? So now again, if I calculate the mid, so this becomes 6 plus 10 divided by 2, 16 divided by 2 is 8. So now this becomes my new mid position. Okay, this one. So now what happens, it checks whether the data value is equal to, the same thing repeats, right? Because we are dealing with recursion, we are calling the same function. So again, the data that is present in this new mid value is checked with the target value. Since the target value matches the data present in the new mid index position, therefore we get a return of true and our program terminates. So this is how recursion in binary search works. This is it for this video. I hope you found this video helpful. Please like this video, subscribe to my channel, and hit that bell icon, because I'm creating a playlist called Data Structures and Algorithms in Python. So you'll be notified every time I upload a new video for you to follow. Okay, so this is it. Thank you so much for sticking by, and I hope to see you guys very soon. Thank you.